Hi everyone, and welcome to this series of videos in which I'm going to teach you how to model an end plate steel connection, which is a type of connection that looks like this one that you see here. This series of videos is part of my nonlinear FEA course, which is available on my website, learnfea.com. I'm going to let the link of this website in the description of this video. And for you to be able to understand everything that I'm going to show here, you should know well about linear FEA theory and nonlinear FEA theory. So for example, for my students that are watching this series, they have went through the linear FEA course, which is a separate course that I have on learnfea.com. And they have went through the theory part of the nonlinear FEA course. So in this course, I have 5 modules focused mainly on theory. So we learned about all types of nonlinearities, such as material, large displacements, large deformations, and contact. And now this series is part of module number 6, in which we're going to start learning how to model more complex FEA models, such as this one that you see here. Okay, so anyways, you should have a good knowledge about linear FEA and non-linear FEA to understand what is happening behind this software. Obviously that you can just copy what I'm doing here and you will be able to create this model even without knowing what is happening. But this is not really valuable because then if you try to do this by yourself in your job, for example, you will not be able to do this. You're going to face convergence issues. You'll not be able to fix it alone because you don't know about theory. You don't know what is happening behind the software. The software is going to be like a black box for you. Okay, so this exercise is going to be valuable for people that know about theory, such as my students, but for people that don't know, it's not going to be valuable. All right. So before we start this exercise, I wanted to talk about the procedure that we're going to follow. I created a separate video to talk about this procedure, but in here I'm going to summarize this whole procedure again for people that are watching this series from YouTube. So first of all, we are going to use a preprocessor software, which is this one that you're seeing here, to build the model, to define the mathematical model. So we're going to use this software here, ANSA. In my case, I have this version v23.1.1. You can use any version you'd like to except version 25, because version 25 is too different. It's very different if compared with this one. So I guess you're going to face difficulties to follow this tutorial. But if you're using version 29, 20, sorry, not 29, 19, 20, and etc. until 24, then ANSA is going to look like what you see here. So it's going to be easy for you to follow this tutorial. This is going to be our preprocessor. We are going to build the model here. We're going to define the mathematical model. And then after that, we are going to output a file from here by using this function, file output Abaqus. And then we are going to generate a file with this extension. For example, here I have this folder with some files. The file that we're going to generate is one with the extension .inp. Then we are going to open up a command prompt like this, and we are going to use a command such as Abaqus j equals and the name of the file, such as the name of this INP file here without the extension. Then we can insert some other arguments such as the number of CPUs that we'd like to use. CPU equals CPUs equals 18 and etc. We can have other arguments here as well. And then when we press enter, I'm not going to do this now because I don't want to run this model. This model is going to be solved by Abaqus. So Abaqus is going to use the finite element method to solve the mathematical model and find the active displacements and the output requests. And then some files are going to be generated in the working folder. So you see here that we have all these files generated for this specific model. And then we're going to use this specific file, the one that has extension .odb, to post-process the results. And then to post-process the results, we're going to use this software here, META. I'm using version 23. You can use any version except 25. And then this software is specialized on post-processing. And then I have here, for example, that model opened in META. And then, for example, I can plot, let me amplify the deformation by 30 times so we can see better how this is deforming. I'm going to plot the stress, for example, and I'm going to animate this and look at how this deforms. So anyways, we can post-process the results in this software by using the file with extension .odb. One important information is that you should have the Abaqus library installed in the META software to be able to post-process files that has this extension. This is important. Okay, you're going to see that if you don't have this library and if you try to input the .odb file here, you're going to this is going to yield to an error. You're not going to be able to post-process it. Okay, so this is the procedure that we're going to follow. So create the model in ANSA, solve in Abaqus, but we are not going to really open any Abaqus application. We are not going to use, for example, the Abaqus CAE application. We are just going to run it through command, and then we're going to get the files that Abaqus generates and post-process in META. Okay, now the next thing that I wanted to talk about before we even start this exercise is how we are going to create these models and in what we are going to base the information that we are going to use. So for these advanced exercises, most of the time I'm going to use a scientific article to extract information. The great advantage of doing this, or one of the advantages of doing this, is that depending on the article that we choose, we have experimental data to compare the results of our simulation. And this is very important because we have learned in the linear FEA course that we have a procedure named validation in which we get the results of a simulation and compare with experimental data. And then we are checking if the mathematical model that we have built in ANSA is actually representing the physical model that in this case is what you see here in this image. You see, this is a physical model. This is a real structure of the real life. And then we want to represent it using a mathematical model of the type boundary value problem, as we know, and solve it approximately using the finite element method. And Abaqus does that for us. So the validation procedure is when we get the results of the simulation and compare with the experimental data to see if, or to check if the mathematical model that we defined actually represents the physical model that we have here. So this is one of the advantages of using articles to base our studies. And the other advantage is that articles study about something specific. In this case, it studies about end plate connection. So when we go through this exercise, we're going to end up learning about this type of connection. Okay, we're going to learn about it. We're going to learn some theory related to it. So whenever we follow an article, we're going to end up learning about something new, which is interesting. So anyways, I guess it's interesting to base these exercises on articles. By the way, for my students, if you'd like me to create a model based on an article that you are studying, or if you'd like me to create any kind of modules, maybe something that you're trying to solve, you can send me a private message or comment in this video. Well, any way you'd like to communicate with me, because the idea is that this is our first exercise. My idea is to always keep creating more and more exercises. Okay. All right. So now let's start the exercise itself. I'm going to base this model in 2 articles. Here we have this first article that we are going to extract experimental data. And here we have this second article that we are going to extract information on how to build the model. These articles are related. They have been written by the same people. You see, we have the same people here. And this one that is related to experimental data was written in 2007, and this one in 2008, 1 year later. Okay, so these are related. But the main article is this one, where we have the information of numerical simulation of steel pretensioned bolt and plate connections. Okay. All right. So before we start gathering information from this article, let me open up this module that is very similar to the one that we're going to create, so that I give you an overview about what we are going to model, and then we can start it. Okay, so the idea is that we are going to create a beam, which is this entity that you see here. Let me see if I can get pro area. No, I'm going to try to isolate. I'm going to isolate this. You don't need to follow anything that I'm doing now. We have this beam, right? This is a kind of entity used in steel structures. This is an I-shaped beam. And then we want to connect this entity to a column, which is another kind of entity used in steel structures. We have this vertical I-shaped beam, which is named as column. And to connect these 2 entities, we can use many types of connections. And one of these types is one named end plate. In this kind, we connect, or we weld this plate that you see here at the end of the beam. We can have stiffeners, which are these triangles. And then we connect this plate to the column through bolts. You see, we have these holes here. In this case, I have 8 holes. And then we are going to have a bolt passing through these holes. We can have stiffeners in the column as well. Actually, for this type of connection, we should have these stiffeners at the columns in the same height of the flange of the beam. And in that way, we are going to have the behavior that is expected for this type of connection. Okay. Now you see that in this case, I have the bolted connection modeled as you see here. We have this coupling and another coupling here, and we have a beam element connecting the couplings. So this is the first modeling strategy that we're going to use. But after that, we are going to also model the bolted connections as you see here, using solid elements. Well, that's why this exercise is going to be, we're going to learn a lot by doing this exercise. You see, there are all kinds of nonlinearities occurring here. Let me animate this. Obviously that the deformation is amplified here, but We have all kinds of nonlinearities. We have large displacements, large deformations. We have contact occurring here in this region, and it's a non-linear contact. It has friction, and it allows separation. We have material nonlinearity, so we're going to have plasticity occurring. And we have a bolt pretension that we need to model. Anyways, this is going to be a very good exercise. We're going to learn a lot by doing it. Okay. All right, so that's the overview that I wanted to start with. Now, the next thing that I want to do is to create the working folder. I have this folder already created in my desktop, and in here I have the two articles that we're going to use, and we have this document with some information about this model. I'm working yet on this document. By the end of this tutorial, I'm going to have finished this, and I'm going to provide it as a guidance for you to follow. Okay, so by the time that you're watching this video, I have this document ready for you. Okay, and then in here, I'm going to create one additional folder. So in your case, you can, in any place of your computer, create a folder with this name, for example, end plate model. Okay, and then this folder is going to be the working folder. We're going to place our files generated here. Just 1 second. Okay, so let's keep this folder here. And now the next step is to open up an empty ANSA section. So I'm going to search for ANSA. You should have ANSA installed in your computer, obviously. And I'm going to start an ANSA section. And then the first thing that appears is the launcher. By the way, you don't need to have any prior knowledge about ANSA, META, or even Abaqus. I'm going to teach you in these tutorials everything that you should know about these softwares. We're going to slowly learn about these softwares by creating these models. Okay. All right. So first thing that we need to do is to choose a layout. You see that we have these options, right? So depending on the type of analysis that we want to perform, we can choose a specific layout. This is just going to make the, this is going to just simply place the buttons that are related to some specific kind of analysis in a more accessible place. I don't really like to use any specific layout. I usually use the ANSA default layout, this option that's already chosen here. And then we don't need to do anything else here. We can press OK, and then ANSA is going to open up. Now we have release highlights. We can close these. And then, well, I'm not going to give you an introduction about the software and explain what we have in the menus, what we have in these buttons, anything like that. I don't really like to teach about a new software like this. I prefer to simply start working with one specific model, and then while we are building this model, I'm going to explain some things here and there. And then if you keep following these tutorials of many exercises that we are going to perform, you're going to keep learning, and there is going to, well, you're going to learn anyways. I prefer to do this like that. All right. So the first thing that we see here is job files here to open. Usually, when we start working in a model, we import a CAD to ANSA. The CAD contains the information about the geometry, the faces, definitions, and line definitions, and etc. This software is not so good at creating CAD, at creating a new geometry. It's good at meshing. It's good at defining the boundary condition. Oh, sorry, the mathematical model, but it's not really good at creating the CAD. So that's why he's saying job files here to open, because he expects a CAD file such as a .step file that was generated in a specific software for CAD, such as NX Siemens, CATIA, SolidWorks, and etc. In this particular exercise, we are going to create the CAD because it's very simple. You're going to see that it's very simple. And also because we're going to end up learning about many things here in ANSA while creating this CAD. I'm going to be able to show many cool functions to do that. Okay, so in this case, I'm going to click here on File and then New. When I do this, I start an empty section in ANSA where I don't have anything defined. The first thing that I wanted to show related to ANSA to you is what you see here on the left side of the screen. Here we have the database. Basically, here we have everything that has been already defined in the module. So you see that what we have here is only this item ANSA part, which is related to the parts. So if I double click here and something is going to be shown here, we have just this untitled part that is empty because we don't have anything here. Okay, and then we have this other item, W plane. These are the working planes that we have defined. So 3 working planes are already defined. If I double click here, in this small window below, we have the working planes defined. So we have this one, it is the XY plane, YZ plane, and ZX plane. Okay, so this is all we have defined, and we need to start creating the entities. Well, before I forget, I need to teach you how to rotate and how to zoom in, zoom out, and etc. To rotate, let me get here this model that has something. To rotate, I need to hold the Control key, and while I'm holding the Control key, I'm going to use the left mouse button to rotate. You see? Now, if I want to translate, I need to keep holding the Control key and use the scroll button to translate. Scroll button, you know, the I don't know how, the middle mouse button, maybe. This is the correct way to say it. And we can use the right mouse button to rotate it like this while holding the Control button. Okay, so left mouse button, rotate, middle mouse button, translate, right mouse button, we rotate it like this. I don't really use this kind of rotation. Zoom in and zoom out, you should use the scroll button, the middle mouse button, you know? Okay, that's all you need to know, I guess. If there is anything else, I'm going to teach when it's needed. Okay. All right. So let's go back to this article. Let's open this article here. The name of the PDF is this one, Sheet 2008. The title is this one. And I'm going to actually open it in this board so I can create some drawings here. Okay, so here you have the article, and we're going to start gathering information in this article. The first thing that I wanted to show is that in this article we have 8 different models. You see, SC1, SC2, and etc. until SC8. We're going to use only one of these models as an exercise here. I guess I'm going to use this one. I'm not sure yet. SC2. Okay, I'm going to define as, well, let's use this one. I'm pretty sure that we're going to use this one. And then we have the connection type extended. So let me explain what is this. You see in this drawing here, this first drawing, this is the connection kind SC1, this one. And the connection type is flush. This is the only connection type of that is named as flush. And it is flush because you see that this plate here that is welded at the end of this beam, it doesn't extend above and below the flanges of the beam. Okay, so when this happens, he's saying that this is a flush connection type. Okay, now you see that in this connection, we have an extension of this plate above and below the flange. You see this extension here. And then when this happens, he's saying that this is an extended connection type. Okay, so we're SC2 is an extended connection type. We are going to have this extension. End plate thickness is 20. The end plate is this plate that you see here. Let me highlight it in this model. The end plate is this plate here. So the thickness of this plate is going to be 20 millimeters. The bolt diameter is 20 millimeters. So we will have these bolts here, and the diameter is going to be 20. We are going to have 8 bolts, just like we have here. You see 1, 2, 3, 4, and 4 below as well. In total, 8 bolts. We have column stiffener. Column stiffener is this. Let me see if we have another drawing here. Yes, in this drawing, he also puts here that column stiffener is these plates that we have here. Okay. And we also have end plate stiffener. End plate stiffener is this rib that we have here, this triangle, below and above. Okay, it is this triangle that we have here, above and below. Okay, so yeah, we're going to use SC2 because it has all of these features. All right, so also we have some information here related to the geometry of the beam and column. I guess I'm going to start drawing the beam and column by using this information. Okay? Yeah, so let's start doing this. I'm going to go back to ANSA, the empty section that I have. And in here, let me deactivate my camera. And actually, I'm going to place my camera. Maybe let me activate it again. I'm going to place it here and a little smaller. All right. First of all, you see that we have these buttons here, right? These are modules that we can choose. This first module, labeled as topo, is used to create geometry or to modify geometry entities. This one is for meshing. This one is also for meshing. By the way, depending on the version of ANSA that you have, maybe you have something a little different than what you see here. Okay, but this one is for meshing. This one is also for meshing, but for volume mesh. This one is for solver tools, and this one is for advanced meshing tools. Okay. By the way, I have in my website, Learn FEA, a specific course for meshing using ANSA. And in this course, I teach everything about advanced meshing techniques. Not only advanced, but well, I teach about how to mesh any kind of part. In this course, we're going to, well, when we get a simple geometry to mesh, I'm going to show you how to mesh it here. But when we have something too complicated, I'm going to simply maybe create a different video to teach how to mesh, but we're going to then use this mesh in our module. Okay. So in case you don't want to know how to create complex mesh, you can simply use the one that is going to be ready. Anyways, the module that I'm going to use is this one. And by the way, you see that we have these buttons here, right? These buttons are related to tools that we have in a specific module. So if I click here, I go to a different module, and then these tools are different. So I'm going to click on this drop down icon, and then I'm going to this classic topo module. And then I'm going to use these tools that we have here. Okay, so as I mentioned, this software is not so good at creating geometry. So you're going to see that it's not so practical to do this in here. First thing that I want to do is to create a new point. Let me deactivate my camera just to be sure that it's not in front of it. You see, I have this group here named points, and I want to create a new point. Left click and hold here until you see these two options, and then select this first option, numerical input. And then in here we can define the coordinates of this point. I want to place it in the x, y, and z equals 0. So I want to place it in the origin of the coordinate system that we have defined here. Click on OK. And now we have this new point created. Notice that in the database, we have this new entity, point. We can double click on it, and then on this place here below, we have this point that has been created. If we double click on it, this card opens, and we have here the x, y, and z coordinates of this point and the ID of this point. Okay. All right. Now I'm going to create another point. And for the definition of this other point, I want to draw the beam at first. So I need this section depth. Let me create here, just for you to understand what is this, I'm going to create here an eye-shaped section like this. This is not looking so perfect, but that's okay. All right, so web thickness is the thickness of this plate. This is the web. Flange width is the width that we have here, 200. So this is the flange. We have the upper flange and the lower flange of the eye-shaped beam. The flange thickness is the thickness of this entity, 12, and also here, 12. And the section depth is this height that we have, 300. Okay, now I want to use shell elements to discretize the domain of this beam. So what I really need to draw is the middle surface of this eye-shaped beam. I want to create a line like this, and another line like this here, and one vertical line like this. And after creating these lines, I want to extrude these lines to create this surface. You're going to understand after we do this, okay? So in this case, the distance that we're going to have between this and this is going to be, let me get the calculator. It's going to be 300 minus half of this thickness minus half of this thickness. So it's going to be minus 12, 288. So this is 288. Okay. All right, let's do this. I have this first point created. Now I want to create another point because I'm going to use these points to create the lines. So I'm going to use this tool here. This tool here, relative, inside the points group. Click on it and then select this point, middle mouse button to conclude. And then I can define a direction. You see, we have dx, dy, dz. I want to create this relative point in the positive y direction. Notice that we have this coordinate system here in the positive y direction. So I'm going to define dy as 1. This is how we define a direction. And we should define here the distance that we want this point to be placed. In this case, I want 200 because I want to create this line that we have here. So 200 and press OK. Now we have this point here. So you see that this relative tool creates another point relative to one specific entity that we select. Very simple. Okay, now we have this group here, curves. I want to create a new curve connecting these 2 points. So create, and then this shows up. I want to create a straight line from here to here. So I'm using the left mouse button to click. And then you see that we have this created, but it's not really created already. We need to use the middle mouse button to conclude. And now this has been created. By the way, there is one important thing here. Let me close this and I'm going to Control Z. And I'm going to activate create again. Whenever we activate a function, or most of the functions that we are going to, well, if it's a function that we are going to create a new entity, such as this one, that we are going to create a new curve, we have some information that appears here on this part of the screen, which is something related to the configuration that we have for this tool. And there is this configuration related to the part, right? I'm going to slowly explain about how this works in ANSA, how the part works in ANSA. In here, let's for now select use existing. So when we create this line, it's going to create this line and assign this line to an existing part in the module. In this case, we have only one ANSA part created. And then it's going to assign this curve to this part. Okay. And then select these with the left mouse button and these, and then middle mouse button to conclude. Now we have this curve created. Close this tool. And now you see, I have a new item here in the database. So basically in the database, we are going to have information about everything that was created. So the database is very important. If you don't see the database, you see that we have these blue buttons above, right? And then we have this arrow here that shows more buttons that we would have, but doesn't fit. In this case, I have the database here. You see that it's activated. So if you don't see the data at the database, you should go here and activate it so that you're going to see these items. Also notice that we have this ANSA part. If I double click on it, in this window below, we have the parts that we have created. We have this untitled part. And this curve was assigned to this untitled part. Okay. We can even name this by clicking left clicking here. And we can name it as AUX ANT, which means auxiliary entities, just to put points, curves, and everything. All right. Now, I want to copy this line in the Z direction with a distance of 288 millimeters. Okay. So to do this, to copy this curve, we can use a tool that we can find here in these yellow buttons. We have this one, transform. Maybe, depending on the size of your screen, you're not able to see it here, so you need to click on this arrow to see more options, and then you're going to find it here. And if you don't find it, there is this search bar that we can search any tool. So for example, if I type transform, it's going to find the tools that has this name. So for example, I have this one, utilities, transform, and copy. This is the one that I'm going to use. And then if I click here, it shows where we can find this tool. So whenever you don't find a tool that I'm using here, you simply need to search here. Okay. All right. So transform, copy. And then I want to copy entity. This is an entity. Select. And then after selecting, and by the way, you see that whenever we activate a function, we have some orientations here that we should follow in this part of the window. So he's saying select any entity. And then I'm going to select this with the left mouse button. It's already selected. Middle mouse button to confirm the selection. And then I want to copy. And then the type of movement is translate. And here we can define the direction. So I want it in the Z direction, sorry. So in the Z, I want to put the number 1. And now in here we define the distance. In this case, the distance is 288. So type 288 here. And then click on the plus button if we want to go in the positive direction of this vector that we have defined, and negative if we want to go in the negative direction. In this case, I want to go in the positive direction, so click on plus. And then this window appears. So he wants to know what we should do with the PID. I'm going to explain what is PID later. Okay, PID is very important. I'm going to explain later. So in here we can simply put no offset, as you see here, and part. I want to create this new entity in the same part. It's okay. And set. I'm going to explain what is set shortly as well. So simply put none here, and then click OK. And now we have this curve created. After creating this curve, we click on Finish. And then the copy function is activated yet. We can close this to deactivate, or you see that we have the copy function here. We can click here, quit copy, and then this is deactivated. And now I want to create one line connecting the midpoint of this one to the midpoint of this one. So in the classic topo module, I'm going to go to the curves group and then create line. And then if I position the mouse here, you see that we have this 0.5 written. This means that we are in the midpoint of this curve. So left click here, and then position the mouse here on this one, and left click on this. And then don't forget to middle mouse button to conclude. Now we have the line created. Okay, now close this tool again, and we have the section definition of the beam, right? And now I need to create a surface by using these lines. And to do this, I'm going to, there is this group, surfaces, and there is this tool, extrude. By the way, you see that we have this error here. And then if I click here, it shows more functions that are in the group named surfaces. So if you don't find a function here, try to search for it in these additional functions. Okay, this is important. So we're going to use the extrude tool, and then left click and hold these to see these other options, and keep holding the left mouse button, and only release on when you select the function that you want to use. So in this case, I want to select extrude. So I'm going to release the left mouse button now. And then we have this that appears. I need to select the extrusion profile. I'm going to select by this kind of entity. In this case, this is a curve. And then I'm going to select this curve, this one, and this one. Simply select it using the left mouse button. There is no need to hold the control button or anything like that. And then the direction profile, we can select curves, cones, and etc. I'm going to explain what is a cone shortly. But in this case, I want to use a vector. So select use vector. And well, for some reason, I was supposed to be able to edit this. Oh, okay. I needed to press the middle mouse button to conclude the selection of the extrusion profile. Now we can select use vector, and then we can define the direction here. In this case, I want to extrude it in the positive x direction. Notice that we have the coordinate system here. So you see that we have dx, dy, and dz. I'm going to define dx as 1, dy as 0, and dz as 0. So we have defined a unit vector in the x direction. And then the distance, let's look at this article where we have this information of the distance. Okay. So in this drawing, we have this distance here of 1200. Let me see if in the other article we have this information as well. Yeah, in this drawing, we also have this information. So it looks like this 1200 is from this plate until this face right here. So this is not really so well defined. What I'm going to do now is to simply define the length of this beam as 1200, and later we're going to adjust it. Okay. So let's define this distance as 1200. And after doing that, middle mouse button, and then accept surface. Okay. All right. Now this shows up, and maybe in your case, I forgot to set up some things here. So let's do one thing. Let's close this, and then it created. Let me close this as well, and I'm going to Control Z. Just to show one very important thing. Now again, extrude. And then you see that in this part of the screen, we have these options. And again, we have part and property. For part, let's use existing. No, let's actually create a new part. So let's ask here to ask always. So it's going to ask us to create a new part. You're going to see. And property, we can use the ask always option as well. So it's going to ask us to create a new property. And then again, select these 3 lines, middle mouse button, and then use vector, 1 here and 1200 here, middle mouse button, and okay. And then you see it's asking us to select a property so that the faces that has been created is going to be assigned to this property. We don't have any property defined here, so we need to create a new one. Right click, new, and shell. And then in here we can name it as, for example, beam. And we can set up some things here, but I'm not going to set up anything here yet because we will need to, I'm going to set up it later, okay, shortly. Here we can define MID, which is the ID of a material, and the thickness, and also the element type, and etc. Let's just click on OK here. And now we have this new item. Double click to select this property. Now that we selected the property, it's asking us to select the part that we want to assign this new surface. And in my case, it opened the model browser as a tab here. But in your case, it might have opened the model browser as a window. Let me left click and hold here and drag it like this, so it opens this window. And then you see that we have only this part for now, that we have the curve here and also the points that we have created. We can assign this new surface to this part as well. Or actually, I'm going to create a new part just to practice. So left click and hold, and then select part. This part is created, left click, and then I'm going to give a name such as beam. And then I'm going to double click on this, and now this surface was assigned to that part. Now he's also asking to select another property, because I guess, you see, it has created this surface with this line, and now it's going to create another surface with the second line. Let's assign this property as well, and this part. You see, it's now created this one, and now I want to create the vertical face. Select this property and this part, and now it has created the vertical face. All right, now we can close this tool, and here we have the surface of the beam created. We can control the visibility of entities by unchecking or checking these boxes that we have in the database. So for example, if I don't want to see these curves, I can go to the curve item and deactivate this option. Right, now I don't see the curves anymore. Let me explain to you about these lines that we have here and the name of the entities that we have here. So for example, we can see in the database, we have this item here. If we double click on it, it has these three entities. These are faces. So we have three faces, right? We have this other item here named cons. Cons is curves on surface, or curve on surface. What is a curve on surface? It is these lines that you see here. These curves are part of a surface, right? Now you see we have curves. These curves that we have created previously, these ones, these are not part of the surface. It was used to create the surfaces, but it's a separate entity. Let's uncheck this so we are not able to see it. Okay. All right. Now let's talk about cons. In this case, I have red cons here, right? For you to see the same thing that I'm seeing, you should be in the topo module. So be sure that you are in the topo module. You have these selected. So the red cons are labeled as single cons. This means that these cons are only connected to one single surface. For example, this one is only connected to this face, right? But there is a problem, because, for example, this con here, this was supposed to be connected to two different faces, to this face and to this face. But since this con is red, this means that it's only connected to one face, that in this case, it's this face here. So we need to find a way to connect then this con to this flange. We are going to do this by using one tool in the cons group named project. Left click here in project. And then I want to project this con, select it. And by the way, before, let's just see one thing here. Oh, okay. Yeah, in this setup, you should have this paste option activated. Okay, so activate paste option. Paste means like a tie, like glue together, connect. So after selecting this con, you see it has this instruction, select cons. Middle mouse button. Now it's saying select face. Select this face, which is the face that we want to create, we want to project the con, middlemost button. And now you see that the color of this line has changed, right? Now it is this cyan color or blue color. When we have this as a cyan color, this means that this cone is connected to 3 faces or more. Double click on face, and you see that this upper flange has split in 2 because we have projected the cone and now we have 2 faces here. And we have also the web, this face. So this means that this cone is part of the web, this face, and this face. So it is part of 3 faces. Okay. Now let's do the same thing for this one. You see now we have only one face. Now project, select this cone, middlemost button, select this face, middlemost button, and now this is a cyan cone. And this face is split in 2. Now we have these 3 faces connected to this cone. Okay, now this means that this beam is completely defined. The faces of this beam is completely defined. Okay, now let's talk about properties or PIDs. We are going to use shell element to discretize this domain, right? And we know that we should define some things for the shell element, such as the kind of shell element, the material used in the shell element, and the thickness of the shell element. These are the main properties that we should define in this case. You see that we have this blue button here, P. This is a list of properties defined. You can access these in here in tools. No, not in tools, in lists as well. Lists, properties. I usually access it by clicking here. When I click on it, this shows up, and this shows the properties that we have. Right? We have only this property that we have created, and this is assigned to all these entities. I want to, well, let's double click on this. And then you see that in here we have the 3 main things are thickness. In this case, it's defined as 1 millimeter. The ID of the material, which is 1. I'm going to show the list of materials shortly. And the element type, which is S. Remember that in Abaqus, one of the most used kind of shell element is the S4, right? Which is a rectangle, or not actually a rectangle, it's like a quadrilateral element with 4 nodes. So when we select S and this underline here, this means that we are actually selecting the S4 element. This underline is because this can be a triangle that has 3 nodes, then it's going to be S3, or a quadrilateral element that has 4 nodes, so it's going to be S4. So this underline means that this can be this is a variable number, S3 or S4. Okay. You see that we have some other options here, but we're going to select S. So yeah, this is important. We are going to, the shell element formulation that we're going to use is the fully integrated finite string shell element. This element is applicable, remember, you can search it on Abaqus manual, the S4 element. This element is applicable for thin shells and also thick shells. We can have finite strings, which is important for nonlinear analysis when we have large deformations. And yeah, that's the main characteristics of this element. It's a pretty good kind of formulation to be used for shell elements. And the thickness here, let's define it as, let me go back to this paper. And the thickness information, we have it here. We have the web thickness and the flange thickness. let's define as 8 this property, and then we need to create another property for a different thickness. Okay, so this property here is going to be for the web. This is for the web. Okay, let's name it as actually beam underline web. And the thickness is going to be 8. And let's click on OK. I'm going to talk about the material shortly. And now let's copy, right click on this and copy. And in this case, I'm going to name it as flange. And the thickness is going to be 12. And you see the idea of this property is 2, because the idea of the previous property was 1. So this field here is for the ID of the property. Click on OK. But I need to assign this property to the flanges, because right now everything is assigned to web. So let me close this, and I'm going to use a tool here inside the faces group, this one named set PID. And then I can select by macros shells. Macro is the same thing as face here in ANSA. So in this case, I want to select this face, this one, and this one. These are the flanges. Middle mouse button, and then let's select this property here, beam flange, double click, and now we have this property assigned to this one. Close this tool, and now let's go to property list again. And you see that we can assign a different color for each property. Right now, the colors are very similar, so let's double click on this. And in here, we can left mouse button and drag it until we find a color that we want to use. I want to use like a green like this. Click on OK. And double click on the beam flange color and maybe something red. Click on OK. Close, and here we have it. Okay. All right, now we are almost finished working with the definition of the geometry of the beam. There is just one additional thing that I want to do here in this video, and then we can continue on the next video. Oh, let's talk about the material. I forgot. You see, I have a material list here. Let's open it. And we have a default material that has been created. If we double click on this default material that has the ID 1, we can double click on it. The material card is going to open where we can set up some material properties. For example, I want to name this as steel. Or actually, let's do one thing here. Let's see if we have the information of the material somewhere here. Here we have the material properties of the bolts. Material properties. Okay, so here we have this text for material properties. So the stress strain relationship for the steel plates was taken as elastically perfect plastic, which means that the stress strain curve that is going to be defined is one that looks like this. Stress strain curve, linear part, and then the modulus of elasticity is the coefficient of proportionality. And the non-linear part is going to be a horizontal line, as you see here. So we're not going to have a strain hardening. The stress is not going to increase with an increase of strain. Okay. All right. We have Poisson's ratio. So let's go back here to this module and let's define the Poisson here. Here we define the Poisson's ratio, 0.3. It's already defined as 0.3. We don't need to modify it. The yield strength and elastic modulus of steel plates thicker than 16 millimeters were taken as this value and this value. In our case, the thickness, let's go back here, the thickness of of the, actually, let's go back here. The thickness of the web is 8, the thickness of the flange is 12. So we need to get properties, these ones, of those for plates thinner than 16 millimeters, being 391. This is the yield strength, and this is the modulus of elasticity. So I'm going to copy this value, and I'm going to paste it here. And I'm going to just erase the comma. So the Young's modulus should be 190,707. Okay. By the way, you know that when we are creating a model for Abaqus, we should select a set of units that are compatible. In this case, as all examples that we have performed, I'm going to select for length millimeters, for stress megapascal, which is Newton per squared millimeter, for force Newton. Okay, so this Young's modulus here is in megapascal, as it's shown here. All right. Here we have a standard value for density. Density is in tons per cubic millimeter. This is a standard value for steel density. We can use it. Okay. Now we need to also define the plastic curve of this material, but let's do this later. Let's not spend time doing this right now, because I'm going to spend some time explaining about some things here in this card in more details. Okay, so right now let's just, and also let's rename this as steel underline for, always try to not use space, use underline for thickness less than 16 mm. Click on OK. And here we have the material defined. It has this ID. Double click and you see the ID of this material is 1. And we have it defined as MID, material ID. Now close and close. Let's go back to property. And in these two properties, double click. And then you see that we have the material defined here. And here we put the ID of the material. So in this case, it's 1. Okay. We can even access a list of materials to select by using the question mark button. As you see, select from list, question mark. Oh, let me just change here the keyboard. Question mark, it opens a list of materials, close. We can press F2 to open the card of this material, press S to go back, and that's it. Click on OK. And the material of this flange is also 1. Click on OK. All right. Now, before we finish this video, I want to create an initial mesh for this beam. Actually, I think I'm not going to do this yet, because I'm going to have this end plate stiffener, this triangle connected to it. And this is going to be here, and it's not going to be a good idea to create the mesh now. Okay. So let's firstly create all the geometries, and then we can start meshing the parts. Okay, and by the way, when we create the shell elements here, since we have defined, I know that this is kind of weird, because we have defined a thickness and the properties of the shell elements in faces, face entities, and this is weird, right? When we create the shell elements using these faces, the properties of these faces are going to be used for the shell elements. Okay. All right, let's save this, and I'm going to end this video. So let's go to this working folder that I have created. So you can create a working folder in your computer. I'm going to Control-C the path to this folder, and I'm going to go to File, Save As, And then I'm going to paste the path here, press enter, and now I am in that folder. And then let's give this file a name, end underline plate. Don't use a space. And then the extension is .ansa, and then click on save. And then if we go back to this folder, you see that we have this new file, the .ansa file. Okay, obviously that's when we get when this is ready, we need to output the .inp file, but this is a file that simply contains this module here, not the one that we're going to use to run the module. Okay, so that's what I had for this video. I hope you are understanding this whole procedure. I know that ANSA is not so friendly at first. You're going to get used to it when you do as many exercises as you can. Okay, so see you in the next video.